Hello everyone. Today let us look into why stacking layers makes AI smarter. So far in this journey, we have built the foundation of how modern AI systems actually work. We started with the basics, what AI, machine learning, generative AI and LLMs really mean. Then we moved deeper into the mechanics. We explored how neural networks process information, how text becomes tokens and how then tokens are transformed into embeddings. We looked at vector databases, how self-attention allows tokens to understand each other, and how multi-head attention allows multiple perspectives to analyze a sentence simultaneously. We compared architectures like BERT and GPT, understood encoder vs decoder models, and learned how models generate text using autoregressive prediction. And finally, we explored different generation strategies like greedy decoding, sampling, top K and top P. But now we arrive at an important question. If one transformer block already works, why do modern models stack dozens, sometimes hundreds? Why? Let's look in today's video. Stack layers. Is one layer not enough? Let's start with a single transformer layer. One layer already does something powerful. It mixes token information, applies attention, and refines the representation of a sentence. In other words, it allows each word to look at every other word and updates its understanding. But it only does this once. Imagine trying to understand a complex paragraph after reading it only one time. Real intelligence usually requires multiple passes of refinement. We observe patterns first, then relationships, then meaning, and that is exactly why depth matters. Because intelligence emerges through progressive refinement, and stacking layers is what enables that refinement to happen. So, what changes as we go deeper? The answer is abstraction. The early layers focus on surface level patterns. They notice things like word order, basic syntax, and local context between nearby words. As we move deeper into the network, the model starts recognizing structural relationships. It begins connecting words that may be far apart in the sentence. It detects subject object relationships and aligns context across longer spans of text. Then the deepest layers move beyond structure into meaning. They capture things like intent, sentiment, topic, and semantic relationships. Each layer makes only a small adjustment to the representation, but when dozens of layers are stacked together, those small adjustments create a hierarchy of understanding. Let us look into how the representation evolves. Same sentence but different depth. Here's a fascinating insight. The sentence going into the model never changes. The words stay exactly the same, but what changes is the internal representation of those words. At the first layer, the vectors mostly encode syntactic information. By the middle layers, the vector becomes context aware. And by the deeper layers, those vectors represent rich semantic meaning. So the sentence itself remains constant, but the model's interpretation of it evolves layer by layer. This continuous refinement is what allows transformers to move from simple patterns to deeper understanding. The architecture analogy. Think in system layers. If this idea feels familiar, it's because we already use the same principle in system architecture. In software systems, we typically separate functionality into layers. The front-end layer handles presentation. The business layer handles the logic, and the data layer manages storage. Each layer abstracts the complexity below it. Transformers work in a very similar way. Shallow layers captures patterns, middle layers capture structure, and deep layers capture concepts. This layered hierarchy allows complexity to be managed and refined step by step, and that hierarchy is what enables intelligence like behavior. More layer is not just bigger. It's tempting to think that adding layers simply make the model bigger. But the real benefit is not size, it's capability. Depth allows the model to extract better feature, build richer representations, and form stronger abstractions. And when networks become deep enough, something interesting begins to happen. They start to exhibit emergent behaviors, abilities that were never explicitly programmed. But without depth, none of this is possible. Because without depth, there is no hierarchy. And without hierarchy, systems cannot develop intelligence like reasoning. Multi-head versus multi-layer. In this series, we have already covered what is multi-head attention. And in today's video, we have seen what is multi-layer stacking. Let's see why both matters. At this point, we can see that transformers actually operate in two dimensions. One dimension is the width and the other dimension is depth. Multi-head attention gives us width. Within a single layer, multiple attention heads run in parallel. Each head focuses on different types of relationships. Syntax, long-range dependencies, entity references, and contextual alignment. It is like having multiple experts examining the same sentence from different perspectives at the same time. But depth comes from stacking layers. Each layer takes the representation produced by the previous layer and refines it further. Early layers detect patterns, middle layers understand structure, deep layers extract meaning. A simple way to think about this is multi-head attention provides many viewpoints simultaneously, whereas multi-layer stacking provides multi-levels of reasoning over time. And when these two mechanisms work together, they create the hierarchical intelligence that makes modern language models so powerful. If you are enjoying this journey and want to build a strong foundation in how modern AI systems actually work, I highly recommend going through the full AI for Beginners course. It walks step by step through the essential ideas that power today's generative AI systems. In the next part of this course, we will explore two very important concepts that directly impact how LLMs operate at scale: attention complexity and the context window. These ideas explain why transformers become computationally expensive and how the amount of text a model can process is fundamentally limited. So stay tuned because understanding these concepts will reveal some of the most important engineering trade-offs behind modern AI systems. Thanks for watching. If this video helped you, hit like, share it with friends and subscribe to Decode Bro for more insightful content. Stay tuned for the next episode. Until then, take care.